Oxidation be the loss and reduction be the pain. Redox, oh baby, gonna bring me that pain.
Redox.
Hey everyone, we're going to talk about balancing redox reactions in this video. So we're going to follow 6 basic steps to balance any redox reaction. Some of them that you encounter will feel a little bit unnecessary, to be completely honest. I had a reaction here earlier, and when you do it, you end up with the exact same reaction or just a slightly balanced version of it. This is one where you'll see a little bit more of a unique answer. So our 6 steps that we'll follow are to write down the unbalanced reaction. We are then going to separate the process into half reactions, and from there we'll assign oxidation numbers, identify and write out all redox couples in the reaction, and then combine those redox couples into 2 half reactions is the idea. Step 3, we're going to balance the atoms in each half reaction. So we're going to balance all other atoms with the exception of hydrogen and oxygen. We're going to make sure that our charges are balanced on both the products and reactant side, and then we're also going to balance the oxygen at the end. We're going to make the electron gain equivalent to the electron loss, and then we're going to add the half reactions together and simplify the equation, removing whatever parts appear on both the products and reactant side. So to start this off, we have step 1 done for us already. Step 1 here is this writing out the reaction. So we're looking at a reaction where we have iron 2 reacting with permanganate to form iron 3 and manganese. Now what you'll notice is this is not a typical looking reaction where we have an obvious single replacement or double replacement. All we're given is the parts that are going to be either oxidized or the parts that are going to be reduced. That's the only components that we're given. And then it's up to us to figure out what other components are needed for this reaction to take place. So if you imagine this as a lab scenario, you'd imagine wanting to generate one of these 2 products using a redox reaction. And what we would do is set up this scenario where we can try to predict what sort of things we need to add into it, whether we need an acidic or a basic solution. We'll briefly mention that in this video, and then we'll go from there. So that's step number 1. I'm going to use these double lines here to indicate a separation of information. So that's step 1. Step 2 is to do the half reaction. So I'm going to write that down here that we're doing the half reactions in this next step. And so if we look at the iron here, we can see that iron goes from Fe2+ to 3+. So it is lost an electron, and loss of electrons, LEO, is oxidation. And so we're going to have this Fe2+ reacting to produce Fe3+ and 1 electron. So I'm writing this electron here so that we can see that we have actually produced or lost one of those electrons, and we're going to try to track and follow where that electron actually ends up going. So I did it in green there, electrons have always been green to me. So this is our oxidation reaction. Another thing you'll notice, I didn't write any of the states. I'm not particularly picky with my students if they write the states because it ends up creating a big soup and a big mess. So that's the oxidation. Reduction then would obviously be, well, the other thing. And the other thing was the MnO4 with the minus charge, and that is reacting to produce Mn2+, like such. And so what we need to end up doing here in this case is we need to end up adding, we add 5 electrons to this. And part of the reason that we add 5 electrons to this is we need to look at the various oxidation numbers that we have present here. So with the manganese, or with this oxygen here, what we're looking at is we're looking at an oxygen that will always have a -2, let's do this always in red, -2 oxidation number. And so overall what we're looking at right now is a -8. And so we need to assign some sort of number to this manganese. And the number we end up assigning then to get this -1 charge is we end up assigning a +7, because 7 minus 8 gives us the -1. And so we have this +7, and we need to get it all the way down to 2+. And so what we end up doing is we end up adding 5 electrons at this stage here. And again, this 5 electrons is only based on the manganese. Again, right now we do not care about the oxygens, we do not care about the hydrogens. We will address those later. Okay, so that's the half reaction step. The next step is to balance out our hydrogens. And this is where it'll be determined whether you're in a acidic or a basic solution. If you are in an acidic solution, you're going to add H pluses to balance out the hydrogens. If you're in a basic solution, you're going to add OH minuses to balance out the hydrogens. Now, obviously, with the basic solution, it becomes a little bit more difficult because you're also adding now just a extraneous oxygen in there, and so we'll need to balance those ones later. So it becomes a little bit more difficult in a basic solution. In an acidic, it's nice and easy because we simply have this hydrogen. So again, we're going to write down our oxidation and our reduction reactions. We're going to write both of those out. So what we had previously was this Fe3 plus reacting to produce, Fe3 plus, this should be Fe2 plus, this should be 2 plus, and we were producing an electron with that. The reduction side, what we were looking at was that MnO4 minus, and we added those 5 electrons again to balance out that manganese charge, and then we ended up reacting to produce Mn2 plus over here. And so what we have right now here is we have a case where the right side of the reaction needs to be equal to the left side of the reaction. And so what you can see is up on this part here, if we compare these two sides, this overall side, the left side is 2 plus, the right side's also 2 plus. We have 3 positive protons here and 1 negative electron, and so those two will cancel out. And if we look at this reaction, however, what we can see is we have 2 positive charges on the right, and we have 6 negative charges on the left. And that doesn't work for us. We need those two to be equal. And so we're going to add a number of hydrogens to make this side also 8H plus is what I would like to write. 8H plus. We want to make both of those sides overall, the overall charge of those two sides, equal to each other. So now we have a -1 plus 5, so that's an overall of -6. And then -6 plus 8 is +2. And so we're left with a balanced reaction in terms of the charges now. Now what we've done is we've generated something where we have too many hydrogens on one side. And again, dependent on whether this is acidic or basic will depend on what you're adding into this actual solution. So next step is going to be adding the H2Os. And we add H2Os to balance out the number of hydrogens. So in that top reaction, we had Fe2 plus reacts to produce Fe3 plus our electron. That one doesn't have any hydrogens, so it's a balanced overall reaction. The bottom one, however, we have MnO4 minus plus 5 electrons plus 8 H pluses reacts to produce Mn2 plus. And what you can see now is that we have an uneven amount of hydrogens on both sides. We have 8 hydrogens on the left, and we do not have 8 hydrogens on the right. So we're going to add 4 H2Os over here to the right side, and that then balances out our number of hydrogens. What you'll also notice, and this is a convenient feature of balancing redox, is that we had 4 oxygens on the left. Those are now also balanced out by this addition of water. It will always work out that way, which is really, really nice for us. Okay, so we used H2O to balance out the number of hydrogens. What we now need to do is just balance both the top and the bottom reactions. And so what I can see as a key problem right now is that this top reaction only is having the movement of 1 electron. The bottom reaction is having the movement of 5 electrons. And if we're talking about one thing being reduced so that another can be oxidized, we need to have equal movements of electrons. And so what we're going to do is basically like you did elimination and substitution in math, you're going to take that whole reaction and multiply it by 5 to make sure that we have an equal number of electrons. And so we're going to end up with 5 Fe2 plus reacts to produce 5 Fe3 plus and 5 electrons. We're going to do our reduction reaction now where we didn't change anything, so it's just MnO4 minus plus 5 electrons plus 8 H pluses reacts to produce Mn2 plus, and 4 H2Os. And so now we're at the stage where we've got both of those balanced, and all we want to do is combine them. We want to combine them. And so what we end up with is we have 5 Fe2 pluses on the left, we have an MnO4 minus. We have a 5 electron. We have 8 hydrogens. And those are all going to react to produce our Fe2 plus, our Mn2 plus, our 4 H2Os, and also now our 5 electrons. And so what you can see now is we have this reaction where we have products being shifted into the reactants. And what we want to look for is we want to look for the things that are the same on both the products and the reactant side. And so usually what I do with my students is I put this symbol underneath them just to say that, hey, those are the same on both sides. So what we end up getting is our final overall balanced chemical equation, which is 5 Fe2 plus MnO4 minus plus 8 H pluses reacts to produce Fe2 plus Mn2 plus 4 H2O. And so what we did here is we started off with this measly reaction and we ended up with this really long thing. We took a couple different steps here. We wrote out our half reactions based on what was oxidation and what was reduction. We then assigned oxidation numbers and added electrons to those half reactions based on the charges of a certain species, whether it was being oxidated or reduced. So because this is being oxidized, we need to add electrons over here. Because the Mn is the one being reduced, we need to add electrons over to the left side. We then took our protons, our hydrogens, and we balanced both sides of the reaction based on where we needed to have both the charges of the products and reactant side be equal. And so here we added 8 hydrogens to make sure that +2 and +2 were what both sides were equal to. Down here, we said, okay, great, we got everything all fine and dandy balanced out, but on this reaction, we used the H2O to balance out the number of hydrogens. And what it also did for us is balance out the number of oxygens. Imagine that. We then went to balancing the number of electrons to make sure that whatever was being reduced was giving up the same amount of electrons as whatever was being oxidized. And so we multiplied this top oxidation reaction by 5. We had then 5 electrons on both sides of the reactions, and we combined these two. Everything on the reactant side went with everything on the reactant side, products and products. We then saw that we had electrons, 5 electrons on both sides, and so we canceled those out and said we can't have something that's both a reactant and a product. That doesn't make any sense. And we ended up with this final balanced chemical equation. That is how you balance a redox reaction.